Good morning, Dr. Yap and Dr. Rida. My name is Idp I am Group 33 Track 7's leader. So in this presentation, we will be talking about our meeting with PPUM after Dr. Yap's advice, why we chose particular materials, our CAD model, and our progress so far, Doctor.
Currently, many pharmacies still rely on stock management process manually. These methods are really time-consuming, inefficient, and heavily dependent on human attention. As a result, pharmacists spend a significant amount of time checking for their inventory and retrieving medications, which increases operational delays and creates a very high risk of human error during dispensing. So, to address these challenges, our project proposes an automated storage and retrieval system designed for pharmacy applications. The system automates the sorting and retrieval workflow by accurately locating and dispensing the medications based on the system command. By minimizing manual handling, the ASRS significantly reduces inventory checking time while ensuring patient safety and a more efficient pharmacy operation, allowing pharmacies to focus on higher value clinical responsibilities.
This is our meeting with PPUM and the email we approached them and the response we obtained from PPUM. The meeting is fixed on last Thursday. These are the photos taken during the interview session at PPUM. The arrangement of the racks and the dimension are taken for the design requirements. Our system needs to manage nearly 900 medicine variants, including cold storage. The absolute priority is FIFO, first expiring, first out. To operate within a tight 1.2 meter AL, we are designing a universal gripper with dynamic slotting, moving away from fixed racking to ensure high precision and space efficiency. Our system needs to manage nearly 900 medicine variants, including cold storage. The absolute priority is FIFO, first expiring, first out. To operate within a tight 1.2 meter AL, we are designing a universal gripper with dynamic slotting, moving away from fixed racking to ensure high precision and space efficiency. Our system needs to manage nearly 900 medicine variants, including cold storage. The absolute priority is FIFO, first expiring, first out. To operate within a tight 1.2 meter AL, we are designing a universal gripper with dynamic slotting, moving away from fixed racking to ensure high precision and space efficiency. Our system needs to manage nearly 900 medicine variants, including cold storage. The absolute priority is the current workflow has a major bottleneck. Locating medicine takes over an hour. Storage is random and purely manual, relying on trolleys and just 3 staff members. There is also a complete lack of data tracking for night shifts, making the operation unpredictable. The current workflow has a major bottleneck. Locating medicine takes over an hour. Storage is random and purely manual, relying on trolleys and just 3 staff members. There is also a complete lack of data tracking for night shifts, making the operation unpredictable. The current workflow has a major bottleneck. Locating medicine takes over an hour. Storage is random and purely manual, relying on trolleys and just 3 staff members. There is also a complete lack of data tracking for night shifts, making the operation unpredictable. The current workflow has a major bottleneck. Locating medicine takes over an hour. Storage is random and purely manual, relying on trolleys and just 3 staff members. There is also a complete lack of data tracking for night shifts. Therefore, we need a flexible solution, not a standard off-the-shelf ASRS. Since tagging every unit with RFID isn't feasible, we will focus on consolidated carton scanning. We plan to use raw supply history to optimize our sorting logic, while remaining mindful of potential budget limitations. Therefore, we need a flexible solution, not a standard off-the-shelf ASRS. Since tagging every unit with RFID isn't feasible, we will focus on consolidated carton scanning. We plan to use raw supply history to optimize our sorting logic, while remaining mindful of potential budget limitations. Therefore, we need a flexible solution, not a standard off-the-shelf ASRS. Since tagging every unit with RFID isn't feasible, we will focus on consolidated carton scanning. We plan to use raw supply history to optimize our sorting logic, while remaining mindful of potential budget limitations. Therefore, we need a flexible solution, not a standard off-the-shelf ASRS. Since tagging every unit with RFID isn't feasible, we will focus on consolidated.
Hello, my name is Idp I'm the leader of Group 33 of IDP Track 7. As you can see, we have requested for raw data and supply history from Pharmacy Smart Sorting System on Thursday after the interview itself, and we have received it on Friday. And due to certain reasons, PPM Pharmacy told us not to share with the public. So what we would do is we would share with coordinators and SSS during week 14 final presentation.
Alright, we have our bill of material. So we have the system overview. You can see the dimensions, the payload capacity, and we have our aluminum as our frame material. And you can see the materials for the structural frame, and you can see the axis materials on your right. And every material is listed here. So as a continuation of the bill of materials, we got the Z-axis system, the Y-axis system, and the software integration that includes all the cameras. You can see all the materials over here, and this will be explained in the CAD drawing later on. Alright, this is our frame structure, which is made by aluminum profiles. And the aluminum profiles are a very common material being used in most design. It's lightweight and it's strong. And you can see here is a cage design so that we can place 2 robots, one on the front and one at the back. And it can accommodate 2 rack shelves. Alright, so we use our NEMA 23 stepper motor for the X-axis and Z-axis mechanism. Why? Because torque output it ranges from 0.5 to 3 Newton meter, and you can see, and we have calculated that the X-axis bell speed is going to be 1.25, which is sufficient, and the Z-axis is going to be 300 to 1,200 RPM, which is plentiful. And you can see the calculators, max lifter mass, and the force as well, which is sufficient. Okay, we use the NEMA 17 for the Z-axis, which is the gripper arm, the suction. And why we use the 17 is because we don't need much torque, and we just need a 0.4 and below. And you can see we have a linear force of 15 newtons, and it's really, really plentiful. And here's the velocity, which ranges from 0.084 to 0.42, which is very suffice because the range of motion is going to be quite less, so we do not need that much speed. We decided to use the vacuum pump for our end effector system because the tote tray has a flat surface, and we do not need to use a complicated gripper mechanism, which we'll needed to calculate all the gripper strength. And so here are the specs of the vacuum pump, a 12-volt DC vacuum pump, and we're gonna have 2 of them to suck onto the tote tray. And here's the operating pressure, the lifting mechanics, all of the specs are over here.
This is the necessary calculations for main driver motor, NEMA 23 stepper motor, speed, mass that it can carry, and then the x-axis value speed, and also calculations for arm drive, NEMA 17 stepper motor, the motor force that it can handle, the maximum speed that it can handle, and whatnot, and then also vacuum pump, the suction force, max mass that it would be able to pull. These are the calculations for the aluminium T profile to show the materials property, the geometric properties, the vertical column, how much of the stability it will be able, the maximum weight it will be able to carry until it completely fails, and also the base thickness to prevent the deflection. So to see, so from our calculation, we get to know that choosing 4080 profile for base makes structure 87.5% more rigid. We also calculated the natural frequency analysis. This is based on our assumptions. We calculated that 345 RPM is where the frame will hit resonance and shake violently. So what is the safe thing we can do is make sure either lower or higher than 345 RPM so that beating can be avoided. This is the analysis we did using SolidWorks on 40x80 base. So as you can see, this is the study results to show that how would the projection be if more stress applied.
So here are the CAD drawings, and on the left is the overview of the entire system, the entire gantry system, and on the top right corner is the x-axis mechanism, and you can see that we use a pulley system. So I attach the NEMA 23 stepper motor on the left, on the right vertical post, and the dummy pulley is attached on the other pulley, and it's attached on the left vertical post, and is connected via a timing belt with the carriage plate, which we use an aluminum plate. And this carriage plate is sitting on top of linear carriage blocks and on top of a linear rail. And that's how we drive the x-axis mechanism. And you can see a detailed view on the bottom, right? Alright, so we have our y-axis mechanism, which is the vertical lift. This vertical lift is driven by the NEMA 23 stepper motor, which sits on top of housing with spacers so that we can access the coupling easier. This coupling is attached so that this coupling attaches the motor with the lead screw, the ball screw. And of course, we have our BK12, it's like kind of like a bearing, so that it makes sure that this ball screw doesn't vibrate violently and expand due to thermal stress. So we have our vertical masses beside the ball screw. Okay, the ball screw sits between these 2 vertical masses, which we use the aluminium beam 3030, and we have this linear rails, linear blocks sit on top of this aluminum beam, so that we can have our nut housing. We have our carriage blocks, which we then put on the carriage plates on top of these components. So yeah, that is the y-axis, how the y-axis mechanism works. So the center is the overview of the y-axis mechanism, right? So we move on to the z-axis, which is our suction, okay, our end effector mechanism, right? So we have our carriage plate. Of course, you can see the vertical one is the one I talked about, and then it has to be an L shape so that we have this mechanism sitting on top of this plate, this base, you can call it. And then we have our suction cup that is attached to arms that we will use an aluminum beam, and then this entire structure, this aluminum arms, the suction is this entire chassis will be driven by a NEMA 17 stepper motor, and it sits on top of linear rails with linear blocks and a timing belt. All right, so the stepper motor will attach to the pulley, which will be attached to the belt. Right, this belt is fixed, and we can it's some sort of like a zip line mechanism where we have this chassis moving along the rails like a zip line. Right, yeah, that concludes our explanation of the CAD drawing.
Our pharmacy smart sorting system is based on the ASRS system, where we use a metric storage approach, FIFO logic, as well as real-time update. So I will explain more about the metric storage approach, where each medication slot is identified by specific row and column coordinates. When a storage of retrieval command is received, the control system processes the requests accordingly. For operations, medication data such as identification, batch number, and expiry date are scanned for storage, and the available matrix position is assigned based on FIFO logic, ensuring newer stock is placed behind the older stock. For retrieval operations, the system searches for the matrix database to locate the oldest valid stock for the requested medication, calculates the optimal movement path, and retrieves the item. After each operation, the matrix inventory is updated in real time, where the stock levels are monitored, and alerts will be triggered if replenishment is required, ensuring efficient, accurate, and FIFO-compliant pharmacy operations.